All right. Good morning again, everyone. I hope you are doing well and keeping safe this morning because medyo nagsisimula na yata umulan ng malakas in some areas, including our town here. So before we begin with Module 4, do you guys have any questions about Homework 4? Again, the deadline would be for the markup would be until tonight, right before midnight. And just a reminder, if you wish to get a markup for your homework, you need to, number one, submit 4 out of the 5 problems before midnight tonight and send me and go to the assignment page for homework for markup and then submit an inline text saying that you want to get a markup, right? So it's just for me to know that you do not plan to submit any other problems, including the 2 extra ones. So yeah. So if you will not submit an inline text for the markup, then I won't be giving you any markup for homework 4. Because anyway, homework 4 will just be computed over 17.5. So you'll get a maximum of 31. Then if you'll get the markup, so you get 6.2, so about 37.2 over 17.5. So I think that would be more than enough for you to catch up, probably with some of the scores that you got in homework 1 and homework 2. But okay, no questions about that? Matatapos na ba homework 4? Okay, but you guys can hear me, right? Baka hindi nyo pala ako naririnig.
We can hear you, sir.
Okay, thank you. No questions? Okay, so if there are none, then let's start talking about Module 4, which is about matrix representation of linear transformations. And in this chapter, we will look at why linear algebra courses, especially those in the undergraduate level, always begin or always focus on studying matrices, right? So usually curricula or math 211 classes are designed to start with matrix algebra, matrix analysis, or matrix in the context of solving linear equations, and so on. And then they talk about different things like towards the end, they talk about matrices being a vector space, and then talking about different properties of matrices, and so on. So in this module, I hope to give you an idea why that happens. Though we said that linear algebra is the study of mappings that preserve the linearity of the vector space, or will preserve the structure of the vector space with respect to vector addition and scalar multiplication. But why do linear algebra courses focus very much on matrices, right? So this module tries to justify that by showing that there is an equivalence. There's a one-to-one correspondence between the set of all matrices over a field and the set of all linear transformation between two vector spaces of the appropriate dimensions, right? And this would serve as the transition for our class from the more theoretical side, where we talk about field vector spaces over abstract sets or abstract operations, towards what you are familiar with, matrices or vectors with components or consisting of real or complex numbers. And with this, we can play with some numerical tools that we have, for instance, MATLAB. Or that's another question that I would like to pose to everybody. I already asked you to try to see if you can access MATLAB 2 or 3 weeks ago. That's why I incorporated in our homework a problem on using MATLAB. But is that okay with everybody? Naka-access ba kayo ng MATLAB? Because, for instance, in homework 5 problem 2, I ask you to include the screenshot of both the code you used written in MATLAB and the command line output, just to see that you were able to calculate or to verify your hand solutions using MATLAB. Okay lang ba yun? Or you prefer us doing everything by hand? Say if we will be working solely by hand computations, then dapat maliliit lang yung matrices na ipapakonsider ko in the succeeding homeworks. What do you guys think? Okay lang ba na we use MATLAB para medyo mas realistic yung mga matrices na pwede nating paglaruan probably next week?
Okay.
Or okay lang? Is anyone meron ba magkakaproblema with that? I mean, will have no access to MATLAB and so on. So if you do not have access to MATLAB, you don't have it on, just let me know. Send me a message, a private message, para let's see how we can adjust for you. If you have access, then that's good. It's a licensed software, pero luckily UP provides license to everybody using your UP email addresses. So yeah, kaya I chose MATLAB. Madali siyang gamitin,
Sir,
free
is
na
it
yung license.
okay. Sir, is it easy to use?
UP.
Sir, is it easy to use?
Yeah, kasi hindi siya katulad nung ibang mga languages na kailangan mo talaga mag-program. Usually single lines lang yung mga kailangan nating code. So yeah. In certain parts of the module here, I included some screenshots. Makikita nyo napakasimple ng mga commands na gagamitin natin. Hindi siya komplikadong code. So yeah. But again, if you have problems, just let me know. Yeah, during doing the exercises or you have troubles doing MATLAB. Another nice thing about MATLAB that I like is napaka user-friendly nung kanyang help interface. So you can just search what is the code say for finding the rank or finding the nullity for a matrix. Then maganda, madaling sundan yung kanyang help file. So yeah. But again, if you encounter any problem, just let me know and I'll try to help you with MATLAB also. All right. Okay. So let's continue and move on with matrix representations. So last time we talked about linear transformations, their properties, their structure. We said that the set of linear transformations, we call it COM VW, is a vector space on its own. We define what this is. So we'll start the module with theorem 27, which right off the bat establishes the equivalence between the set of all m by n matrices and the set of all linear transformations from a vector space of dimension n to a vector space of dimension n. So here we consider two vector spaces. So we have a vector space V, a vector space W, and we have the same underlying field F. The underlying field here will be crucial. You'll see later why. And then we have predetermined dimensions for V and W. So in all that is to follow, we will assume that the vector spaces are finite dimensional. So V has dimension n and has dimension m. Then we will select a basis, call it B for V, and a basis D for W. Then with those choice of bases, there will exist an isomorphism between the set of all homomorphisms onto the set of all matrices, and let's call that isomorphism phi sub BD. And you see the way the isomorphism was named. It was named phi, usual name for isomorphisms, but there's a subscript here which contains B and D, which are the bases that we chose for V and W. So the name alone for the isomorphism promised in the theorem tells us that that isomorphism will depend on the choice of bases for V and W respectively. So you will see later that if you will choose a different basis, or even if you rearrange elements of your chosen basis, then you will come up with different matrices, because the equivalence is always dependent on the choice of the basis for the vector spaces V and W, right? So let's see how it is proven here. Okay. So the theorem is kind of an existence theorem. It tells us that there exists an isomorphism. So the proof is via construction. We will try to construct an isomorphism. So first we need to define what the function phi would be, argue that it is well defined, and then we'll show that that function phi is an isomorphism. So it is a linear transformation that is bijective. In other words, it is a linear transformation that is one-to-one and onto, right? Okay, let's see the proof. So here I started with laying out the premises, and then I chose the ordered basis, the basis B for V, and basis D for W. And note that since I know that V and W are of dimensions n and m respectively, so I can label the elements of basis B to be V1 until Vn, and then elements of the basis D from W1 until Wm. So exhaustive yung listing no basis elements. And then again, it's a proof by construction. So the first thing we need to do is to construct the map, right? So here I'm claiming that the map that will take a linear transformation, right? Because the isomorphism we claim to exist is from the set of all homomorphisms onto the set of all matrices. Then kailangan ko ipakita how this isomorphism will act on a linear transformation. So I'll take an element of the domain, call it L. So ano kaya yung posibleng image ng linear transformation? We expect that image under phi to be an m by n matrix. Okay? So here I'm saying that the phi of L with respect to the bases B and D is the matrix Aij. So hopefully you're now familiar with our notation for matrices. By the way, we are using brackets for matrices. So just a random choice. We could have chosen parentheses, pero let's stick to brackets. So Aij is just the matrix A11, A12, A13, and so on until A1n. Then A21, A22, and so on until A2m, 2n, until AM1, AM2, until AMN. Okay. Yun lang yung notation natin. And what this transformation phi does is it assigns to the homomorphism L the matrix Aij, where the entries Aij are the coefficients, are the corresponding coefficients in the basis expansion of the image of a vector from the basis of V. Okay, so don't worry, we'll see later how this homomorphism works. But basically, yung ginagawa niyo lang, kukunin mo yung, para makuha yung image ng isang isomorphism L, ang gagawin ko, kukunin ko yung image ng lahat ng basis elements nung vector space V. All right? And then I would look at how is the image of a basis element of V is expressed in a basis expansion using the basis elements of W. Right? So yung mga VJs, galing siya dun sa basis ni V. Ipapasok ko siya sa linear transformation. Of course, this image is an element of curly W, right? Kasi image na siya dun sa codomain. So this goes to W, but W is a vector space, so that means this element, L of Bj, can be written uniquely as a linear transformation, as a linear combination of elements of the basis for W, right? Yung mga Wi's element siya ng basis ni W. So that means this representation is unique, and to get the entries in my matrix, the ijth entry, the entry on the ith row and jth column of the matrix representation for L would be consisting of the ith scalar in the expansion of the image of Vj with respect to the basis elements of Wi. So ganun yung nangyayari. Get a vector in the domain, in the basis of the domain, si Vj, computein mo yung image niya under L. Tapos pag na-compute mo na yung image ni L, kailangan mo kunin yung basis expansion ng image with respect to the basis D. Okay? And then that coefficient that you get, that scalar coefficient for each of the Wi's will serve as your corresponding entry in the matrix. That's why you see this will be an M by N matrix. Kasi ilang VJs meron? V's dimension N. So we will have N elements there. So si J ay fixed. So we will have N columns because the coordinates of the image of Vj will be on the jth column. And then we'll do this for all terms in the expansion of LBJ with respect to D. That's why we will have M rows. All right. So medyo it takes some time to get used to how phi is defined, but don't worry, there are a lot of examples, probably 3 or 4 in the module, showing how exactly this phi works. But for now, just bear with me and let's see how the proof goes para lang makita nyo how we establish the equivalence between Hom VW and the set of all M by M matrices. Okay. Now I mentioned earlier that this expansion is unique, right? That's one of the theorems we have. If you have a basis, there will exist a unique expansion for any vector in the space with respect to the basis chosen. So that means the AIJs are uniquely determined for each of the VJs, making this matrix well-defined. Okay, so indeed phi is a well-defined function. And then the next step is to show that phi is bijective, right? So we want to show that this is bijective. So what we'll do is first show that it is monic. To show that it is monic, let's assume 2 elements of the domain of the map phi, right? Let's call them L and M, such that they share the same function value. So remember, pagpapakita ng one-to-one, gusto kong ipakita that eventually, if the images are equal, then the pre-images L and M are equal to each other, right? So I'll suppose that they have equal images, they have the same matrices, and then if that is the case, then by definition, LVJ will be equal to MVJ for all J, right? So if that is the case, ibig sabihin, L and M have the same action on the basis elements. All right? Eh, anong sabi natin sa linear transformation from before? We said that the action of linear transformations is completely determined their actions on the basis elements. But this statement over here tells us that L and M acts on the basis elements of V in exactly the same way, right? And if they will act on the basis elements in the same way, in exactly the same way, therefore L and M must be equal to each other. All right? And that's how we conclude that phi is monic. All right? Any questions so far? Okay lang ba yan? All right. Now let's go to the second part. Nag-freeze din ba yung screen ko with you guys? Ayan, move na siya. Okay, the second part is to show that it is epic. Tapos na yung pagiging monic or pagiging one-to-one. Let's now show it is epic. Now to show that it is epic, we want to show that any matrix in any element in the codomain is a image, right? Kasi para maging epic, dapat yung range ay equal sa codomain. Ang codomain ni phi ay set of all m by n matrices over F. So we want to show that any matrix, any m by n matrix with entries over the field F has a preimage. Okay? Now, let's try to construct it. So, given ngayon yung matrix, gusto mo yung corresponding or meron bang corresponding linear transformation for it? Now we note that every vector in VE can uniquely be written using this basis expansion. Mukhang nag-freeze na naman ako. Yep. But I hope, guys, my audio is good. Or napuputol din ba?
Sir, okay naman po.
So yung ano lang, yung screen ko lang ang delayed. Or anyway, right. So here, again, the idea, mag-start tayo sa matrix. Gusto ipakita may linear transformation ng image under phi ay yung matrix na yon. Para mapakita ko na yung range ay equal sa codomain. O para mapakita na onto yung mapping phi, right? So we'll start with a linear, a basis expansion for V. Let's say it's the sum of alpha j vj going from 1 to n. Okay. And then with this basis representation for any element V, I can define a mapping L from V to W such that L of any vector in V is the sum of Aij is a constant. This would be the coefficients coming from the matrix that you were given before. Alpha j is the coordinate of V in the expansion with respect to the jth basis element Vj. And then this will serve, or this scalar will serve as the coordinate of the image with respect to the ith basis element in W. So ganito ko dinidesign yung matrix, yung linear transformation na gagamitin yung entries ng given matrix from above. So meron ako matrix Aij. Alam ko lahat ng element ng domain. Gusto ko ngayon mag-define ng linear transformation L, such that when I take phi of L, dapat makukuha ko ay yung given matrix Aij. Okay? Now, the trick is, alam natin na L of the pyramid in a unique way. It will have the scalars alpha j's. Okay? Then, what I'll do is I will have that alpha j multiplied by elements from the jth column of Aij. And then I'll take the sum of all those products. Okay? So this is well defined. And then this product, this summation of Aij alpha j will be another scalar in F. And I will use that scalar in F to be the coordinate of the image LV with respect to Wi. So kaya kung makuha to, siya yung magiging multiplier dun sa mga basis elements ni V. Basis elements ni W. Okay. It is quite straightforward to show that L here is a linear transformation. Okay. So dahil linear transformation na siya, gusto ko na lang ipakita na masasatisfy niya yung required property. What is the required property in definition 55? Phi of L is equal to Aij if and only if LVJ is equal to the sum of Aij Wi. So that's from equation 55. So that means I need to check what is the image of a vector of a basis element under the linear map L that I have just constructed here. Medyo malala na pala yung delay dun sa screen ko. Wait guys, let me just try to fix this. Okay, so going back here, so we have defined a linear transformation L. So what remains to show is that this linear transformation L satisfies definition 55 or equation 55, which is how we define phi of L. All right. So note that uh, definition 55, if we go back to it, so equation 55 here. Equation 55 requires that the image of a basis element Vj must be equal to this sum, right? Tapos kinlane natin dun sa second part ng proof natin for being a bijection is that we have a linear map L, which we define this way. So I need to show that this linear map L satisfies definition 55 or equation 55. But definition 55 only talks about what is the image of a basis element. Okay. So meron tayo ditong Vj. All right. So what would be L of Vj? So I'll plug it in. So what will happen? I'll plug Vj in here. Okay, and let's see what its image is. But the image under L depends on how you expand your element, right? But note that if I have a basis element, say Vj, right? Yung basis expansion niya ay magiging sum lang ng alpha j pa rin times V, sorry, let me use a different letter here. Let's say Vk, alpha j Vj, j going from 1 to n. Yan yung basis expansion. Pero dahil si Vk ay isa dun sa mga basis element, so its expansion with respect to the basis I, yung coordinates niya ay puro zeros except for one element, which should be the unity, right? And that will happen when k is equal to j. So pag ikukunin ko yung sum, expand ko lang yung sum, alpha 1 v1 plus alpha 2 v2 plus alpha k vk hanggang makarating ako sa alpha n vn. Tama? So, ibig sabihin, para makuha ko si vk, dapat lahat ito ay 0. This must be 0, this must be 0, this must be 0, except for alpha k, which should be equal to 1. Right? That's the expansion of a basis element. And that's what I said in here. Alpha k will be equal to 1 if and only if k equals j, and otherwise, everything will be 0. Okay? And then dahil si alpha k ay equal lang kay 1 kapag ka si k ay equal kay j, what will happen to this sum? So that means it will just turn out to be a single term, right? Kasi yung mga alpha j's malamang madalas silang 0 except for one case when k is equal to j. So therefore, this guy will just be aij times 1 plus aij times 0 plus aij times 0 and so on. So what will be left will be aij times 1, and that's what we got here. Okay, so this shows that the way we define the transformation L here satisfies definition equation 55, right? So which is our ansatz or our guess for the linear transformation phi, how to get the matrix for a linear transformation L, okay? And that shows that whatever I choose or whatever matrix I choose, I can always define a linear transformation L exactly in this manner that satisfies definition 55. And so that proves that the range of the linear map phi is equal to indeed the set of all m by n matrices over F. Okay. Okay, that is epic. That is monic. Yeah, I guess I missed one part of the proof here. I should have also proven that that phi is a linear transformation. Kasi sinabi ko that phi is an isomorphism. So para maging isomorphism siya, dapat siya ay epic, dapat siya ay monic, saka dapat siya ay a linear transformation to begin with. Let me see. I think I did not. I haven't proven that it is a linear transformation. But I think that that comes naturally out of the way we define phi. Maybe let's give the proof a shot here. Okay. Let me just copy this just to complete everything. Okay. Now, what we want to do here is to show that phi BD is a linear transformation, right? It's a linear transformation from the set of all homomorphisms onto the set of all m by n matrices, okay? Pakita na natin yung monic, napakita na natin yung epic. So what's left to be shown is that it is a homomorphism to begin with. So in order to show this, I want to show that vector addition and scalar multiplication are satisfied or are preserved. So what I'll do is to take two elements of the domain of phi. Phi is coming from the set of all homomorphisms. So that means I will take two linear transformations from hom VW over the field F. And we want to show that phi BD of L plus M is equal to phi of BDL plus phi of BDM. Okay. So yan yung gusto nating ipakita to show that it is or that it preserves vector addition. So let's try to see that phi of BD of L plus M actually is what? By definition, this is the matrix ano ba yung mas madali? Mukhang mas madali if I start with matrices. Kasi ipakita na siya ay nandito. Alright, let me see. Yeah, mukhang mas madali yung pakabila. Or tingnan ko muna how L plus M works on elements of the basis. So let's see. Let's try. So let Vj be an element of the basis for V. Okay. And then note that L plus M of Vj, by definition of function addition, is L of Vj plus M of Vj. And then let's assume that LVJ is equal to the sum of AIJWI, going from 1 to M, plus let's use BIJ WI, going from 1 to M, for some AIJ BIJ coming from the field F. Okay, so here I am supposing that LVJ is the linear combination with respect to the WIs with coordinates AIJ, and MVJ is the vector from W with scalars Bij with the coordinates Bij with respect to the basis elements Wi's. Okay. And then here we see that in all, we can write this using properties of summation as Aij plus Bij times Wi's. All right, so I can simply expand them into one big summation and then use the distributive property of scalar multiplication over vector addition to get this form, right? So here we see that phi of L plus M actually is the matrix consisting of Aij plus Bij, right? Because remember, phi of a matrix, phi of a linear transformation is just the bunch of coordinates we see here, okay? And in this case, we see that indeed the coefficients for L plus M of Vj is equal to the sum of Aij and Bij. So the matrix representation for the sum of L and M is equal to this guy, right? But we can easily break this down into the sum of two matrices, Aij plus Bij. And Aij, the way we define, or we have chosen the Aij's, this is basically phi of BDL plus plus phi of BDM. Okay. So this proves that vector addition is preserved. Okay. Now the argument for the scalar multiple is similar. So I'll just note that here. The argument, and you can try out. You can try to write it out. But the argument to show that phi b of alpha L is equal to alpha phi of L, or in other words, that is if phi bd alpha L, let's do it L, is equal to the matrix Aij, then what you want to show is that phi bd of alpha L is equal to alpha Aij. So it's the matrix whose entries is just scaled by the scalar alpha. All right. And I think the proof would be similar to what we have done for to show that vector addition is preserved. All right. So that just showed that shows that indeed there is an isomorphism between the set of all linear transformations and the set of all matrices over the field of scalars. All right. And one important takeaway from the proof of theorem 27 is that really the matrix representation or the matrix equivalent of a linear transformation really depends on the choice of bases for both B and D. All right. Now, the highlight of theorem 27 is not actually on the result itself, but on the mechanism. Actually, importante rin pala yung result, but almost equally as significant is the proof, because the proof gives us a mechanism in order to construct the matrix representative for a linear transformation, right? And that's what we will do in the next couple of examples, show how to get the matrix representation of a linear transformation and vice versa. Okay. Now let's start with example 49. In this example, I considered the vector space R3 to be both my V and W, and took the field R to be the field of scalars. Okay. And I think in a previous example, example 33 in particular, I've said that any scalar defines a linear transformation. So just for an easy and quick example, let's just consider a simple linear transformation that is scalar multiplication or scaling of a vector. So in particular, if I define D to be the doubling map, meaning it will just double every element of every component in my vector, right? So D is the map from R3 to R3, such that the image of a vector from R3 is just double of its components, right? Kaya tinawag ko siyang D for the doubling map, okay? And then let's illustrate how we can apply the proof of theorem 27 in constructing the matrix equivalent for the doubling map. Okay. Now, Theorem 27 tells us crucial yung choice ng basis. So first, we need to elect basis for V and W. It just so happened in this example that I chose V and W to be the same vector spaces R3. And luckily, we know an easy basis for R3. So as our first example, tingnan natin yung matrix representation with respect to the canonical basis. So the canonical basis for R3 is just this guy, E1, yung vector na meron lang 1 sa first component and 0 elsewhere. E2 has a unity or 1 in the second component and 0 elsewhere. And then E3, siya naman yung 1 sa third position, 0 elsewhere. And let's use this canonical basis in order to find phi D sub EE. Ibig sabihin, the matrix representation of D with respect to the basis E for V and E for W as well. Okay? Now, in order to do that, and this is what I'm trying to explain earlier, paano natin mahanap yun? Kailangan ko malaman how the map D acts on the basis elements of the domain. All right? Our domain is R3. We chose the canonical basis for R3. All right? So in order to find the matrix representation, I need to see how D acts on elements of the basis E. And you will see later that the ordering in which I compute the images really matter for the matrix representation. So here I'll stick to this ordering. This is E1, this is E2, this is E3. Okay, I'll compute the images of these basis elements under D. Okay, so here I computed D of E1. Okay, so siya lang yung double of the matrix 1, 0, 0, and that's going to be 2, 0, 0. All right. But remember that the element of the entries in the matrix is actually determined by the coordinates of the image. Remember yung Aij natin kanina in equation 55 depends on the scalars we use in the representation of the image with respect to the chosen basis. So alam ko na yung image ng basis element 1, 0, 0 ay 2, 0, 0. But I need to express 2, 0, 0 using the basis chosen for the codomain. It just so happened that I also chose the canonical basis for the codomain. So the basis, the expansion of 2, 0, 0 with respect to the canonical basis for the codomain is this guy. All right. And then sabi nung definition 55, the AIJs will be the coordinates of the image of basis elements. So here we see yung coordinates ng image ng basis element E1 ay 2, 0, 0. Alright? So kokolektahin ko yung scalars na yon, yung coordinates ng DE1 with respect to the basis for the codomain, and they will serve as the elements A11, A21, and A31. And look at the indexing here. The index 1, the second index here, the second indices 1 here, pertain to what is the basis element number from the codomain that we are dealing with. So I am dealing with the first basis element for the domain. So kaya yung mga second index dito sa mga AIJs ay equal kay 1. And then the first indices here, 1, 2, 3, represents ano yung scalar number dun sa representation ng image with respect to the basis of the codomain. So yung image ni E1 ay pwede kong isulat as 2 times first basis element of W plus 0 times second basis element of W plus 0 times third basis element of W. And that's why A11 turned out to be 2, A21 turned out to be 0, and A31 turns to be 0. And again, I need to be particular here with the ordering. because you will see later that the ordering really matters. So in short, the AI1s are the coordinates of D, they should be D, E1 with respect to the basis E of the codomain. All right. And then I will do this for all other basis elements. So I'll compute D of E2. All right. But E2 is just 0, 1, 0. Apply the doubling operator D. The operator D just doubles all the entries. So we will be getting 0, 2, 0. Now to get the matrix entries, I need to find the expansion of 0 to 0 with respect to the basis of the codomain. Again, it just so happened that I chose the canonical basis for the codomain. All right. And then I'll take the coordinates 0 to 0 in the proper order. So that means the first scalar here will be A12, the second scalar will be A22, and the third scalar will be A12. So, oh, that should not be A12, that should be A32. Okay. So, yung second index, again, represents pang ilang basis yung ginamit natin from the domain. This is the second basis element. So, yung mga second components ay 2. And then the first scalar in the expansion of the image will be the first entry in that column. Etong second, siya yung pupunta ron, at yung third, siya yung pupunta ron. Right? And here you will see bakit yung dimension ng domain dapat ay n, at yung dimension ng codomain dapat equal kay m. Kasi yung mga, kung pang ilang basis element siya, yun yung ginagamit ko as the column number. Okay, so that's why the domain or the dimension of the domain must be the column dimension of the corresponding matrix. And then lastly, I'll do that again for the third basis element with respect to the basis for the domain. Kukunin ko yung image ng basis element na yon. Tapos pag nakuha ko na yung element na yun, kailangan ko siyang i-expand using the chosen basis for the codomain. I will harvest the coefficients, and they will be A13, A23, and A33 respectively. Again, column number is 3 because we are on the third basis element on the domain. And then the first, the row numbers here will be pang ilang siyang coefficient nung expansion with respect to the codomain. And then we'll just need to arrange those coefficients into a matrix, and you see that we get the matrix 2, 0, 0, 0, 2, 0, and 0, 0, 2. And this is the matrix representation of the doubling operator with respect to the basis EE. Okay? Right. Any questions? I hope you see the pattern kahit medyo magulo yata yung pagkaka-explain ko. But a thumbs up, guys, if you get the idea. Or if you have questions, just raise your hand. Parang trivial yung ginawa natin kasi we have chosen the canonical basis for both V and W. Medyo pangit dun sa example, parehas yung domain and codomain. Tapos parehas pa yung basis na pinili ko. I was just thinking to show the easiest example, though it might sound trivial, but I hope you get the process. Let's take it a notch higher in the next example, but hopefully you get the process. Magiging tedious siya pag napakalaki ng dimension ng domain and the codomain as well. But nevertheless, this will pay off later, as you will see. But before going to the next example, let's see how we can use the matrix representation in order to get the image of the linear transformation, the image of an element of the domain under the transformation D using the matrix. So kahit kalimutan nyo na yung doubling operator, how D was defined, if you can remember how the matrix representation looks like, then you can still evaluate D of V for any V in curly V. Okay, but first, what does this matrix does? So what it do is it will assign to a given vector the image under the doubling operator D, but in what sense? Well, what we need to do is that this matrix will serve as a prem-multiplier to the vector consisting of the coordinates of an element V. And I want to stress that ang imumultiply natin sa matrix representation ay hindi yung vector V na hinahanapan natin ng function value. What I need to multiply to the matrix representation is the coordinates of the domain element with respect to the chosen basis. Okay? What do I mean by that? So for instance, gusto kong makita ano yung image ni V, specifically 1, -3 pi, with respect to the doubling operator. Of course, if you know that D is a doubling operator, so expected na natin yung D of V is equal to 2 -6 pi, right? Kasi madali lang naman yung pagkaka-define ng doubling operator. But in case you don't know what the doubling operator is, pero alam natin yung matrix representation niya, so tingnan natin paano siya mako-compute. But before that, yes, Ma'am Rina, you have a question?
Sir, yung po sa pi, bakit hindi po naging 2 pi?
Yung pi, dun sa image, dapat 2 pi siya. Sorry. Hindi ko ba nalagay yung 2 pi? So dapat dapat 2 -6 2 pi. Yun yung expected answer natin. All right? Thank you, ma'am, for pointing that out. So again, I mentioned the matrix phi of D will act not on the vector from the domain, but it will act on the coordinates of that vector with respect to the chosen basis. So hindi ko pwedeng i-multiply to theoretically dun sa matrix para kay D. Kasi number one, mag-act yung D sa field of scalars. So it will act on F to the N and not V. So bago ko gamitin yung matrix representation, kailangan ko munang hanapin ano yung coordinates ni V with respect to the chosen basis. Luckily, for this example, I stuck to the canonical basis for both V and W. So madali lang hanapin yung coordinates ni V with respect to the canonical basis. So dahil si V, pwede nating isulat as 1e1 plus -3e2 plus pi e3. Then we see that the coordinates of V with respect to the canonical basis is this element of, F to the N. Element of F to the third. All right. And you see the difference. So we started with an element of R3, which is our vector V. All right. But the matrix representation will not act on V, but it will act on F to the dimension of V. So kaya kailangan kong munang i-derive ano yung coordinates ni V with respect to the chosen basis. And what I'll get is this guy, which is an element of F to the 3. Kasi yung coordinates kasi nanggagaling lang siya dun sa field of scalars. And you see the subtle change in notation, though mukhang hindi pa siya masyadong clear for this example, but in the next examples, it would be clear. I use brackets for vector elements in R3, but here I am using parentheses para dun sa coordinates. So itong coordinates na to, element siya ng Fn or F3. Yung vector elements, manggagaling siya kay R3 or kay V. All right. So again, from now on, I will use parentheses to denote coordinates. At ang laman niya lang ay mga scalars. Okay? Kaya manggagaling dun sa field. And so, if we want to evaluate D of V, what I'll need to do is to multiply to prem-multiply. Prem-multiply kasi dapat nasa una yung matrix representation times the coordinates. All right? And that's what I did here. I have the matrix representation, but I multiply it to the coordinates. This is what we derived before, okay? The matrix for D. And then this is the coordinates for the vector V that we're trying to evaluate the image of, right? And then if you do the usual matrix multiplication, you'll get this guy, okay? And you see here that kamukhang-kamukha na siya nung ina-expect natin na image ni V under the doubling operator. But you see the notation I used here. I chose parentheses instead of brackets when I told you that I will always use parentheses for coordinates and brackets for vector elements, right? But since the numbers 2, -6, and 2 pi are enclosed in parentheses, so that means this is not the actual image d of v, but this is the coordinates of the image with respect to the chosen basis. Okay? So hindi to yung final answer as d of v. Ito lang yung coordinates ng d of v with respect to the second basis. Alright? So kailangan ko siyang i-convert. Okay? So siya yung coordinates. So para makuha ko yung actual d of v, kailangan kong kunin yung expansion gamit itong mga coordinates na to with respect to the second basis. Again, it just so happened that the basis for w is also the canonical basis. Then I will use the first coordinate we computed in the matrix multiplication. This is the second component of the coordinates we got after the matrix multiplication, and this is the third one, right? So if you see, ito lang yon, tas ito lang yon. Right? Tapos ginamit ko silang multiplier dun sa W1, W2, and W3, which came from our choice of basis. And once we do the multiplication, we get the expected output. So that means we have computed d of v using the matrix representation, even without knowing that d is a doubling operator. Okay? And as I mentioned, this example is quite trivial kasi pare-parehas yung kinuha kong mga basis. And not just na pare-parehas or parehas yung basis for v and w, they are the canonical basis, which makes finding the coordinates very easy, or the transition between coordinates and the vectors themselves are very natural. Kaya ang tawag sa kanila canonical basis. Kasi napaka-natural or canonical nung conversion mula sa coordinates papunta dun sa actual vector. Okay? Now, I introduced some notation here just to have a shorthand dun sa conversion mula sa vector papunta dun sa coordinates. So, pag meron akong vector v, okay, tapos nilagyan ko siya ng subscript curly b, ibig sabihin kukunin ko yung coordinates ni v with respect to the basis b. So, ang sagot sa v sa b ay element ng f to the n. Ang laman niya ay mga scalars na nanggagaling dun sa field such that v is equal to the sum of alpha i's, vj's, j going from 1 to n. So kinukuha ko lang yung mga scalars, tinatawag silang coordinates, and I will collect them all into a column vector, element of f to the n. Okay? So, sinulat ko pala siya dito. So yung mga alphas, sila lamang yung scalars dun sa basis expansion ni v. Alright? And I have a spoiler here saying that the indexing for the basis is important. So we'll see that later in the next example. And conversely, if I have a coordinate, a set of coordinates, say alpha. So kung si alpha ay alpha 1, alpha 2, alpha n, tas gusto ko siyang i-convert dun sa vector, talagyan ko lang siya ng superscript b. I use the superscript to be the basis name kasi nakadepende sa basis yung coordinates. So kung meron akong coordinates, ni-raise ko siya sa basis b or nilagyan ko siya ng superscript b, this will just give me back the vector, all right? Which is obtained by taking the linear combination of the alphas multiplied to the corresponding basis element. So yeah, yun yung magiging conversion natin from coordinates to vector and vice versa. Okay. All right. Let's try equation 50. Example 50. For example 50, again, we will be working with a doubling operator from R3 to R3. But in this example, I will play a little bit with the ordering of the basis for the domain. So remember from before, ang basis natin for both V and W is the canonical basis E1, E2, E3. Paano kung paglaruan ko yung E and form the new ordered basis E prime? Yung E prime siya ay si E2, E3, and E1. Ginumble ko lang yung ordering ng canonical basis elements. All right? And let's try to see, let's compute phi of E prime E, or the matrix representation of D with respect to the ordered basis E prime for the domain and E for the codomain, and see how it differs from phi E we got from example 49. Okay? So again, the first step, how to build a matrix? Well, compute the image of the basis elements under the operator D. Okay? Pero remember, I am choosing E prime to be the basis for the domain. So I look at E prime and evaluate the image of every elements of E prime in the order they were listed in the set notation. So umpisan ko siya sa DE1. This will serve as my V1 kasi siya yung una dun sa listahan ng basis para kay V. Okay? Now DE1, D is just the doubling operator, so I know it would be 0 to 0. Okay? And then to get the entries in the matrix representation, I need to get the expansion of 0 to 0 with respect to the basis of the codomain. Note that I chose the canonical basis in the right order to be the basis for the codomain. So kailangan kong expand this 0 to 0 with respect to the basis ng codomain. Okay? So, but 0 to 0 can be written as 0E1, 2E2, and 0E3. Okay? And so that means yung coordinates ng DE2 with respect to the basis E ay equal kay 0 to 0. And if you notice from the previous example, the coordinates for the first basis element for the first basis element comprises the first column of the matrix representation, right? So pag kinolek ko yung coordinates ni D of the first basis element ng domain, makukuha ko si 0 to 0, and this will serve as the first column in my matrix representation. So that means A11 is 0, A21 is 2, and A31 is 0. And then I'll do this again for the remaining basis elements for the domain. So DE3, kasi si E3 yung pangalawa sa listahan ng E prime. So kukunin ko yung image niya 002. Tapos kukunin ko yung expansion ni 002 with respect to the second basis o yung basis ng codomain. Ang basis ng codomain, canonical. So E1, E2, E3. And the coordinates of DE3 with respect to the canonical basis is 002. And 002 being the coordinates of the image of the second basis element of the domain will serve as the second column in the matrix representation. And then similarly, we'll do it finally for the third basis element of the domain. Use the definition of D in order to get its image. Find the expansion of the image with respect to the basis for the codomain. Harvest the coordinates. And that coordinates will serve as the third column in the matrix representation. Okay? And then now we will assemble our matrix representation, and we will get this guy. And this guy, phi E prime E, is different from phi EE. Kasi yung phi EE, nakita natin kanina, siya ay 2, 2, 2, tapos 0 na siya elsewhere. Right? But this time, we get this matrix. So if you mess up the ordering of the basis, then the matrix representation will also vary. So that's why from now on, we will, whenever talking about matrix representations, we will refer to the basis as ordered basis. Kasi yung listing ng elements ng basis will be important because they will determine the ordering of the columns of the matrix representation. All right. Okay. Let's see how we can use this in order to compute the image of the same vector we used in the previous example. So let's find d of 1, -3 pi, and of course we know we are expecting 2, -6, 2 pi to be the image. But let's forget about the doubling operator and use the matrix representation. Okay? But again, I hope you remembered that the matrix representation will act not on the vector itself, but on the coordinates of that vector. So if I want to get the image of 1, -3 pi with respect to the operator d using its matrix representation, I first need to find the coordinates of that vector with respect to the chosen ordered basis, right? So remember, ito yung gusto kong i-evaluate, ano yung image niya under D, but the chosen basis or chosen ordered basis for the domain is E prime. So kailangan kong kunin ano yung coordinates nitong vector na to with respect to E prime. And it just so happened that the scalars will be -3 pi 1. Kasi V, this guy, would be what? -3 times V2 plus pi, not V2. This is, ano nga yung ordering ng E prime? Si E prime ay E2, E1, and E3. Tama nga ba? I think this is right. So kailangan kong kunin yung expansion ni 1, -3 pi using the ordered basis. E2 plus E1 plus E3. Okay? Tapos fill in the blanks. Not E3. Yeah, tama. E3. Di pala E3. Parang baligtad. 2, 3, 1 nga ba? Check na nga natin yung E prime. Oh, there you go. Si E prime ay 2, 3, 1. E2, E3, and E1. 2, 3, 1. So, ibig sabihin, 2, 3, 1. 2, 3, 1. Okay. So you will see that this expansion will require the first scalar to be -3. Para magkaroon ka ng -3 times E2. Si E2 ay 0, 1, 0. So we will get a -3 in the second component. That's correct. And then we'll have pi here. Si pi, namumultiply siya sa 0, 0, 1. So walang contribution sa first and second component. Contribution sa third component would be pi, which is what we got here. And then finally, E1 will be 1 because E1 is 1, 0, 0. Okay, so that's why this is the coordinates for 1, -3 pi with respect to E prime. Okay, now we have the coordinates. Then what we'll need to do is to multiply the coordinates by the matrix representation. Okay, now if you do the multiplication, the usual matrix multiplication, what you will get would be the coordinates of the image with respect to the basis. So pag minultiply ko to, ang makukuha kong vector, dapat gamitan ko ng parentheses. Just to remind us na this product here, the matrix vector product, is actually a set of coordinates and not the vector itself. All right? So, para makuha ano yung image, actual image ng given vector, I need to translate these coordinates using the ordered basis for the codomain. So ito yung compute natin coordinates. Ang notation ko, ina-upper E ko lang siya para ma-expand siya with respect to the basis E. Alright? And if you do that manually, you'll have 2, the first entry in the first coordinate times the first basis element plus -6 times the second basis element plus 2 pi times the third basis element. Kasi yung ordering ni E ay E1, E2, and E3, just the canonical basis. And if you expand this out, you will get this guy, which is exactly what we expect since simply the doubling operator. All right? Is that good? So again, this emphasizes that the choice of not only the choice of basis is important, but the ordering of the chosen basis is also important, right? So kaya ordered basis lagi yung ginagamit natin para sa kanila. Okay? So ready for a more complicated example? Ibahin naman natin yung basis para sa isa sa kanila. Okay? Okay, let's write 51, example 51. In example 51, let's consider the basis B consisting of 1, 0, 0, 1, 1, 0, and 1, 1, 1. I guess in previous modules, we have established that this is indeed an ordered basis for R3. Tas kunin ko yung phi of E prime B of D. Ibig sabihin, I am interested in finding the matrix representation for the linear transformation D, which is the doubling operator we defined in example 49, but this time with respect to the ordered basis E prime of the domain and the ordered basis B for the codomain. Okay? And again, always the first step. Look at the action of your transformation on the elements of the ordered basis for the domain in the right order. Okay? Again, remember that E prime is just a reordering of the canonical basis. It's E2, E3, and E1, right? So unahin ko tingnan paano nag-work yung canonical base, yung doubling operator kay E2, right? That's what I did here. I guess we did it before in example 50. But the difference here is that though I get the same image, I need to compute what will be the coordinates, but this time with respect to the ordered basis B that we have now chosen for the codomain. All right. So see 0, 2, 0, which is the image of the first basis element of the domain. Kailangan kong kunin yung coordinates with respect to B. Si B1 ay 1, 0, 0. Si B2 ay 1, 1, 0. Si 1, 1, 1. Kailangan hanapin ko yung scalars that will give me 0, 2, 0. Okay? And you can use a solver for a linear equation to find those coordinates or to find those scalars. And you will see that indeed alpha 1 would be -2, alpha 2 would be 2, alpha 3 will be 0. And remember, these coordinates, okay, will be written inside parentheses, all right? And then this guys, -2, 2, 0, will serve as the first column of the matrix representation. That's why A11 is -2, A21 is 2, and A31 is 0. All right? And then again, I'll do it for the other basis elements, again, in the right ordering. The second basis element for the domain is E3. Take its image. After computing the image, find the coordinates of that image with respect to the basis B. Now again, I'll need to find how can I write 0, 0, 2 as a linear combination of 1, 0, 0, 1, 1, 0, 1, 1, 1 in that order. And then whatever the first scalar is, that would be my first coordinate. Second scalar is the second coordinate. And third scalar is the third coordinate. And then this set of coordinates serve as the second column of the matrix representation. Kasi siya yung coordinates ng image ng second basis element with respect to the ordered basis B. And then you'll also do that for the third one. And finally, you'll get this matrix representation. All right. And let's see how this works, right? So let's try to evaluate again the same value or the value of the same vector, 1, -3 pi, with respect to the doubling operator, but using this matrix representation. Okay. Again, pag gusto nyo gamitan yung matrix, kailangan mag-work kayo sa coordinates. So first thing is, maybe I use a different notation here, right? So the image here under the doubling operator of a vector, right, is matrix times the coordinates of your domain element with respect to E prime. Tapos pag na-multiply ko na sila, kailangan kong i-convert into a vector. Kasi yung product na to ay coordinates lang. So yung coordinates, kailangan ko i-convert into a vector. Okay? But before that, in order to take care of this product, I need to find the coordinates of the vector. Yung given vector, i-convert ko sa coordinates. Coordinates niya with respect to E prime is this guy. Ito yung kinompute natin dun sa previous example. And then carry out the multiplication. But bear in mind that the product of the matrix and the vector consisting of coordinates is another set of coordinates. That's why they are enclosed in parentheses. So this is a set of coordinates. To get the vector equivalent for it, I need to translate it or use this as the coefficients in an expansion with respect to the ordered basis B. All right. Remember, basis B is 1, 0, 0, 1, 1, 0, and 1, 1, 1. All right. This is an ordered basis. First coordinate is multiplier to the first basis element. Second coordinate, multiplier to the second basis element. Third coordinate, multiplier to the third basis element of the codomain. All right. And then if you will compute this, you'll get this guy, 2, negative 6, 2 pi, which is what we expected. So this means that although the matrix representation depends on the ordered basis, the result after performing the matrix multiplication and the conversion to vectors will be the same across all representations, right? Which is what we expected or what we want, because we want to have a representation for the same linear transformation. So it means that whatever process we do, the end result should be the same for all these matrix representations. Okay. All right. Any questions before we proceed? Perhaps we'll proceed to maybe the last example for the day. Any questions? Okay, naman. All right, so let's look at example 52. For example 52, this illustrates theorem 19 and remark 4, which is kind of what you're supposed to do for extra problem 1 in homework 4, right? So in this case, I am defining a function f from the set of from the chosen basis to W, and use this to define a linear transformation. Okay. Now this time I chose V to be R3. So my domain is the set of all vectors in R3, and I chose the ordered basis 1, 0, 0, 1, 1, 0, 1, 1, 1. Though this is more complicated than the canonical basis, but I chose them just for purposes of illustration. And whenever we're talking about ordered basis, okay, so pwede nyo na siyang isulat this way. And since we're talking about ordered basis, this is already implied that 110 is B1, 110 is B2, and 111 is B3. Okay? And then my codomain is the set of all matrices, or the set of all 2 by 2 matrices with complex entries. So and then I'll choose the ordered basis P for the codomain. This is the poly basis, which is what you encountered in one of the homeworks. Isa siyang basis for M2C. All right. Then let's call their elements. Bakit kulang? P1, P2, P3. Dapat may P4. Hold on. Ginamit ko ba siya sa baba? Yeah. This should be, yeah, kulang ng isa. May P4 dapat doon. Okay. Great. So the poly basis. And then sabi natin from Theorem 19, pag meron kang function na nag-a-act dun sa basis elements, makaka-induce siya ng isang linear transformation. So if I say that that function f, which acts on the basis elements and maps it into an element of w, then magkakaroon ako ng linear transformation. Suppose that that function is this guy, log of a plus b plus c, cosine c, a plus bi, and pi to the abc. That's how the function f acts on the basis elements, all right? And that is sufficient to build up a linear transformation. I don't need to know how f will act on all elements of the vector space, right? So, but remember, this function f only acts on the basis elements. Ang domain ni f lang ay yung set of basis elements. Hindi ako pwede mag-plug in ng vector v into f kasi wala siya sa domain. So, ito lang ay yung action ni f dun sa basis elements. And it will induce a unique linear transformation L such that L is given by this guy. And this is what Theorem 19 taught us, right? So, L of V, if you have an arbitrary vector, then ito yung pag-compute ng image niya, which is just the summation of the the summation of the products of the coordinate times the function value of the basis element. So yan yung linear transformation. And I want to express this linear transformation as in terms of a matrix, okay? Now, if you'll be patient enough and to compute this guy, right? So f of b1, I see 0, 1, 0 by definition of f, right? Ito si f. Ang first basis element natin ay 1, 0, 0. Ito dapat yung magiging image niya. Then if I plug in 1, 1, 0 into f, this is what I'll get. And lastly, if I plug in 1, 1, 1, which is b3 into f, this is what I'll get. So these are the images of the basis elements under f. And then since we said that L for an arbitrary vector v is the sum of scalars times f of bi, then if I have a matrix V, or if I have a vector V with coordinates alpha 1, alpha 2, and alpha 3, then the mapping L will give me back this matrix. Okay? So si log ng 2 to the alpha 2, 3 to the alpha 3, and so on. So equation 58 tells us how to get the function value of an arbitrary vector. But that representation depends on the coordinates alpha 1, alpha 2, and alpha 3. Okay? So this is the definition of L. Now, let's try to see how the matrix representation for this for this linear transformation looks like. Okay? Again, the first step. Find the image of basis elements of the domain to get the columns of the matrix representation. Okay? So I'll start with that. Computing ko yung L of B1. Ano yung function value ng unang basis element? But I already know that that is f of B1. And I want to write f of B1 in terms of a summation of scalar multiples of the poly matrices, right? So si P1, P2, P3, P4, again, sila to, yung mga poly matrices. Gusto kong ipakita, or I want to see how f of B1, which turns out to be, what is f of B1? 0, 1, 1, 1. Paano ko ito masusulat as a linear combination of the poly matrices? All right. You can use here, again, this will give rise to a system of linear equations, but you can use the result you got from homework, from one of the homework problems. I think I wrote that here. In homework 3, problem 4, you showed that the set of poly matrices is a basis for M2C, right? Tapos dun sa proof nyo ng proof nyo na ini-span niya yung M2C. You computed for the coordinates, how to get an arbitrary matrix A, B, C, D in terms of a linear combination of the Pauli matrices. And that's the formula I used here. You can revisit your answers to homework 3 problem 4, or take a look at the answer key, how I got 1/2, 1, -1/2, and 0. But again, that will just be solving a system of linear equations. All right. And so with that, I can harvest the coefficients, put them into in a set of parentheses, and that will give me the set of coordinates for LB1 with respect to the Pauli basis. And this will serve as the first column for my matrix representation. And then I'll repeat the process, but this time look at the action of L on the second basis element. Now, again, compute LB2, but by definition, that will just be FB2. But F of B2 is this guy. All right. In order to get the second column of our matrix representation, I need to see how can this be represented using the Pauli basis, right? So, again, yung Pauli basis natin ay ito. How can I write this matrix as a linear combination of the Pauli matrices? Okay. Again, you can consult your answers in homework 3 problem 4. In case you didn't get homework 3 problem 4 right, you can take a look at the answer key I provided. That's how you will get, this is your first coordinate, this is your second coordinate, third coordinate, dapat pala dito, second coordinate, third coordinate, and fourth coordinate. Okay? And so the second column for the matrix representation will be this guy. Okay? And then you'll conclude your solution, or first part of your solution, by computing LV3, expressing it as a linear combination of the Pauli matrices, then harvesting those coefficients as your coordinates. Okay? And then you can assemble the matrix representation, and that will be this one. All right? Questions? I hope you are now getting the hang of the process. Medyo komplikado yung example kasi komplikado yung pinili ko na basis. I used the Pauli basis instead of the canonical basis. But again, that's intentional just to show you the process, okay? But if you want a more convenient matrix representation, then choose the canonical basis. Then probably I'll say a word or two later about why choose complicated basis instead of the canonical basis, right? All right, all good? Now we'll finish this example off by using the matrix representation, phi L, with respect to BP, to evaluate the image of a vector V under the linear transformation. Okay. Now suppose we want to get the image of 1 negative pi e with respect to L. Of course, one route is to work with the definition of L, right? And I think the definition of L is in equation 58. So we simply need to plug in, the coordinates alpha 1, alpha 2, and alpha 3 of V, the given vector V, into equation 58 to get the image matrix. Right? Pero suppose I don't want to do that, I'll use the matrix representation. So again, the first step is to find what is the coordinates, or what are the coordinates of the given vector with respect to the chosen basis B. And if you do that, you'll find that the coefficients will be this, okay? And I need to multiply it to the matrix representation. So matrix representation times coordinates of the vector whose image we want to evaluate. We'll get a product, but that product is a set of coordinates. So if I want to get the actual image of the vector, I need to convert this coordinates to the vector using the poly basis. Okay, so poly basis, this times P1 plus this times P2 plus this times P3 plus this times P4. I'll add those four matrices up, then I will get this guy. Okay. Now, it would be a good exercise to compare this with what you would have gotten if you used equation 58 in order to evaluate L of B. Of course, bearing any arithmetic error I might have committed, so kindly double check that. But that's how exactly matrix representation works. All right. So again, there is an equivalence between the set of all linear transformations and the set of all m by n matrices, where m is the dimension of the domain, and n is the dimension of the domain, m is the dimension of the codomain. To find the matrix representation, number one, you need to find how the linear transformation uh, works or acts on basis elements in the proper order. The coordinates you get from that would be the first column of your matrix representation, and so on. Now, the matrix representation will act not on the vector space, but they will act, or the matrix representation will act on coordinates. So matrix multiplication times coordinates. Then the result is another set of coordinates. So to get the actual image, you need to convert that coordinates using the second ordered basis, right? Or the ordered basis with respect to the codomain. All right. Yeah, and I guess we can stop here for today. So any questions? Medyo mahaba yung process, especially if you choose a complicated basis. But why choose a different basis other than the canonical basis? Probably I'll end there. But okay, here we go. The reason why we are looking for different bases instead of the canonical basis is that the resulting matrix using the canonical basis might be ill-conditioned or ill-posed. So we say ill-posed, or oh, maybe I'll phrase it this way. A matrix is well-conditioned if you have coordinates v and v prime that are close to each other. Then AV is also close to AV prime. So if you have two vectors V and V prime that are close to each other in some way, and how the norm in your vector space is defined. So if V is almost the same as V prime, then the matrix A will be well conditioned if AV is also close to AV prime. So yun yung sinasabi natin na well conditioning, or being a well-conditioned matrix. But if it so happened that V and V prime are almost the same, but AV is not almost the same as AV prime, then that's the case that A is ill-posed or ill-conditioned. In practice, we don't want ill-conditioned matrices because a very small deviation in the post multiplier will cause a very big deviation in the product, and we don't want that to happen. If time permits, I'll show a couple of examples about conditioning of matrices. But yeah, but for now, trust me that the choice of basis oftentimes is also crucial. That's why we want to explore alternative basis other than the canonical basis. But most of the times, the canonical basis is fine. But in cases that it is not, that the resulting matrix is not well conditioned, then we might resort to either finding another matrix representation, but with respect to other ordered bases, or to use some preconditioning techniques. Okay. But let's stop there. But I guess even with that discussion, you'll be able to answer homework 5 problem 1. Okay. This problem gives you vector space V to be R3 and vector W to be the set of all polynomials of degree 2 or less. I gave you the basis 100, 110, and 111 for the domain, and the canonical basis for the codomain. I gave you how L acts on the basis elements of your domain. And then what I'm asking you to do is to find the matrix representation of L. And then you are free to choose one specific ABC in the domain that is not equal to any of the basis elements. Or actually, meron palang specific conditions on A, B, and C. So A must be an integer, B is an irrational number, and C is any real number. So yeah, A, B, C has these 3 conditions. So magkakaiba kayo dapat ng example and show and illustrate how to use the matrix representation in order to evaluate L of V for your chosen V. So isa lang V na specific yung kailangan yung ibigay. Gamitin yung matrix representation para mo-compute yung L of V. All right? And then problem 2 is about nullity and rank, which we didn't have time to finish today. So maybe I'll say a word or two about that next meeting. And then, yeah, ito yung sinasabi ko how easy it is to use MATLAB. In module 4, I included two MATLAB files that you can open and play with. Pero ito yung makikita nyo pag in-open nyo siya in MATLAB. Maybe I can, if you have time later, you can start exploring MATLAB. But this is how the code I used looks like. Entering a matrix A. Ito lang yun. This is an input for the matrix -1, 0, -1, 2, 4x4 pala to, 2, 0, 2, 0, and 1, 0, 1, -1. So yan yung matrix na yan. All right. So I put some comments there para malaman nyo ano yung ibig sabihin ng bawat line ng code. Okay. Then the nice thing about this is nagmamano-mano tayo ng reduced row echelon form, diba? For those who remember RREF, but in the second half of the module, I discussed or I recalled what RREF means. So pagkuha ng reduced row echelon form ng isang matrix sa MATLAB, ito lang. Ta-type nyo lang RREF of your matrix A. Dapat nakadefine na nga lang yung matrix A from above. Just call the routine RREF. Put A inside the command. This will give us the matrix B, which is the RREF or the reduced row echelon form of the matrix A. Tapos pag gusto nyong kunin yung rank ni A, rank of A. Tapos the nice thing about MATLAB, it can also give me a basis for the kernel of the matrix A. Ano yung ibig sabihin ng kernel ng isang matrix? We'll talk about that later, pero I just want to give you a heads up para ma-explore nyo yung MATLAB. Yung null of A, ibibigay niya hindi yung nullity kasi sa atin ang notation natin nullity of A, null of A is the nullity of A, meaning the dimension of the kernel. But MATLAB knows null of A to be finding a basis for the kernel of A. So pag nirun nyo lang, i-display niya ito yung matrix A na in-input ko kanina. Tapos remember B is RREF of A. I-reduce row echelon form ni MATLAB yung matrix A. Ito yung output niya. Tapos ko-compute niya yung rank. Ang rank daw ay 2. We'll see later how to find the rank manually, but MATLAB will just give us the rank right away. And then Z is a basis for the kernel. MATLAB says, oh, this would be your first basis element for the kernel. This is the second basis element for the kernel. And since MATLAB says that the kernel has two elements, right? Ibig sabihin yung dimension ng, the basis for the kernel has two elements. That means that the dimension of the kernel is equal to 2. So kaya mabe-verify natin yung rank nullity theorem using MATLAB as well. Okay? And yeah, that's how I think easy MATLAB is. So kaya ngayon pwede ko, if you agree, we can work with interesting large matrices. Kasi hindi nyo naman gagawin yung computations by hand. So pwedeng mag 20 by 20 matrix tayo. Pwede yung RREF niya, kukomputin lang naman ni MATLAB, and so on. Okay? Now, there's a question here. Ano ang difference ng canonical basis sa standard basis? Parehas lang po sila. I think that's how other textbook calls the canonical basis. Tawag din nila standard basis. Yeah, choice of words lang po. Yeah. So they are exactly the same. Ano nga bang ano ang synonym ng canonical? Kasi parang napaka-technical term ng canonical, no? Kaya usually gusto kong gamitin yung canonical kasi ano siya, parang matalino sounding yung word. Pero canonical, ibig sabihin niya lang natural or standard. So canonical, standard, natural basis, they are just all the same. But when we talk about canonical basis or standard basis, we assume the natural ordering, E1, E2, E3, and so on. Kasi nakita nyo from example 50 na kahit i-consider nyo yung canonical basis, pero paglaruan nyo yung order ng basis elements, may iba yung matrix representation. So when we refer to the canonical basis, that means the canonical basis with the natural ordering, or the standard basis with the natural ordering, and so on. All right? Okay, then I still owe some of you the feedback for homework 4. I'll try to go back grading later today. So yung mga nag-submit probably late last night and starting 8 p.m. and onwards, hindi ko pa sila na-grade. I'll do that later this afternoon. Okay. And then, yeah, any questions? Any concerns?
Sir, tungkol sa MATLAB, sir.
Yeah, hello, sir.
Yung sa MATLAB, sir, friendly ba to, sir? Kasi it is my first time to visit MATLAB. So, pagdating ko doon sa MATLAB, sir, MATLAB, siya, mayroon ba siyang friendly, sir, tips on how to use?
Yeah. Maybe if you want, I can walk you through the code. Na pakita ko yung actual MATLAB interface para magkaroon kayo ng idea how it works. So let me just open my MATLAB.
Sige, sir. Salamat, sir.
You're welcome po. Let's see. Let me just open MATLAB and share my screen. Okay. Okay, so I hope you guys see my MATLAB screen. So when you open MATLAB, you'll be greeted with this interface. So if you want to write a new code, you can click on New Script over here. I hope nakikita nyo yung cursor. Hold on, let me open my, okay, go. Open ko lang yung isang monitor. Okay, there you go. Yep. So I think you can see my cursor here. So you can click on New Script over here on the top left. Then the equation, the code editor will pop up. So ito lang yon. Then you can type. This is where you will type your code. But I will open yung sinend ko na MATLAB code. Maybe I'll open this. Wala na pala siya sa desktop. Pero let me see, open. Okay. All right. So you have your editor. Tapos dito kayo magsusulat ng codes, ng syntax. I will provide syntax, so don't worry. You will just need to modify it a little bit, probably change the matrices or the given values. But ipro-provide ko naman lahat ng kailangan yung syntax. No fancy programming required here. So you will see here, example 55. This is what I sent to you along with module 4. So here is how I inputted matrix A. Negative 1, 0, negative 1, 2, 2, 2, 0, 2, 0, 1, 0, 1, negative 1, right? So, and then this A will just display the matrix A. This is one thing. After each line, so typical programming format, only one command per line, okay? So laging yun ng isang command lang per line, and then you can end the line by a semicolon. Pag semicolon yan, hindi mag-output si MATLAB ng kahit ano for that line. Though it will perform the instruction, but it will not display any output. So this is for suppressing the output, which you usually would like if you don't want to see partial results. But in the end, if you want to see how the matrix A looks like, you can ask MATLAB to display it. So yung disp of A, it will just display the content of variable A. Okay. And then in this line 15, I computed the reduced row echelon form of the matrix A, which MATLAB already knows kasi from top to bottom yung pag-run ni MATLAB. I-run na ni MATLAB si line 9. So alam na niya sa line 11 ano yung itsura ni A. Nakastore na sa kanya na siya yung matrix na yon. And then in line 15, it already knows that it needs to find the reduced row echelon form of A. Yung RREF ay built-in kay MATLAB. So alam na ni MATLAB anong gagawin pag naglagay ka ng RREF. Parentheses, dapat nasa loob yung matrix na gusto nyong kunan ng RREF. Okay? And then, para makompute yung rank ng isang matrix, ang kailangan nyo lang sabihin kay MATLAB ay rank of A. Tapos para makahanap ng basis para sa kernel ni A, kailangan nyo lang sabihin si MATLAB, find the null of A, or the null of A, and store it in a variable Z. In line 19, you ask MATLAB to compute the rank of A and store the result in the variable R, and so on. So, susulat ka ng code. Something like this. Usually, I will give you all the codes that you need. You'll just need to change the matrix A. Parang ganun lang yung magiging programming or MATLAB exercise natin. All of the codes will be provided, all the syntax. I'll also include some comments in here para malalaman nyo ano yung ginagawa ng bawat line. And then MATLAB also has a very good documentation page. So if you want to do something but you don't exactly know how to do it, you can go to the upper right-hand corner, somewhere near that. Meron dyan search box. Say gusto kong malaman ano yung rank. Okay. So maglalabas siya dyan ng different options about all the ranks that MATLAB knows. So rank, it will give you rank of a matrix. If you click on it, it will lead you to a page. Offline naman yung help page. So makikita niyo yung kahit kayo ay walang internet connection at the moment. It will give you ano yung ginagawa ng syntax na rank, the basic syntax. It will also give you ano yung ibang options na pwede nyong ipagawa sa kanya. It even comes with nice examples. So 3x3 matrices, hanapan niyo ng rank. Sabihin niya rin, kasi bibigyan ng mga description. It even has some information about the things that you are computing. So for instance, MATLAB describes the rank to be the number of linearly independent columns in a matrix. Okay. It also says that the row and column rank of a matrix are always equal, something that we will mention next time. and so on. Okay. Tapos, you can also open para makita paano yung example dun sa help file looks like as a live script. So, ito lang papakita niya, okay, calculate 1, kino-compute niya C1. I just click run here. Okay. So kapag ka nasa live script which is sort of a high-tech thing MATLAB does, pwede nyo gawin line by line yung code. So ito yung code niya for the matrix. Ito yung nakuha niya. When you compute the rank, you will see this thing. Okay. So iraran nyo na yun, and then you will get the expected values for those 55. Okay. So, magsusulat kayo ng code or I will provide you a code and then usually if you open a code editor or if you created a new script, yung taskbar sa taas, papakita niya tong options na to. Pero if folder kayo, I'll change the folder. Okay. Pag mag-run kayo, dapat doon yung MATLAB directory nyo ay nandun sa folder kung saan nyo sinave yung file. Pero madali lang naman kung naligaw na kayo somewhere, diba, nasa ibang folder na pala ako. When I hit run, MATLAB will complain na mali yung folder. So just click change folder para automatically dadalhin niya and then it will give you the results in a command window. So yung command window siya, nasa baba, nandito yung results ng lahat ng computations nyo. Okay, hold on. Let me just CLC. CLC, i-clear niya lang yung command window para lang yung mga previous computations ay hindi ko na makita para lang clear. So you can type CLC, the command line, press enter, then go back to your code, press F5 or press the run button. Bibigay niya tong in the command window. So the first would be the display of matrix A, yun yung output niya. And then the next line, I computed B, RREF. I notice sa line akong semicolon. So that means MATLAB will display the result of that line. That line told MATLAB to compute the reduced row echelon form of A and put it in the variable B. So
Sir, nawawala po yung audio niyo.
yeah. Yeah, hello. Sorry, medyo naputol ba? Saan ako naputol?
Sir, may mga ilang parts.
Ako medyo malaki. Okay, so pakibalikan na lang po dun sa recording. Hopefully hindi naman putol yung recording. Pero yeah, I was just talking about the different line commands in MATLAB or how it corresponds to the result in the command window. Okay. So here, yeah. So sa line 19, pinakompute ko kay MATLAB yung rank and call it the variable R. So in the command window, you will see R equals 2. And then yung huli kong pinagawa kay MATLAB line 22 to find null A. If you search null A, in the or if you search null in the help search box, you will see the option for null. Click on it. It will give you a description of what null of A does. So here it shows that Z equals null A is the syntax, and it returns an orthonormal basis for the null space of A. And then for now, you can think of it as a basis for the kernel of the matrix A. Pero i-discuss pa natin siya in detail next time. Just for those who want to explore MATLAB in advance. And then I think MATLAB here has some additional information, okay, about this. Couple of examples. And then it also includes some application examples. What do we need the null space for? So nakalagay din dyan yung mga examples. You can copy paste this into your MATLAB shell or open it as a live script para makita nyo how it works. Then it also has some friendly links here, say RREF, yung mga related na code sa kanya. So you can click on RREF and then show how RREF works, detailed examples, and so on. That's what I love with MATLAB. Napakaganda nung kanyang documentation or the help files that you can access even if you are offline. So 55 and 56 our next meeting. And then hopefully by then turns. Yeah, I also suggest try opening MATLAB, at least open the files that I uploaded at the most. Then tell me on Saturday if you have any problems with it. All right. Wala na po. Okay, so let's end it here. Thank you guys for coming today. Let's see each other again on Saturday around the same time, 11:30. And yeah, I hope you enjoy. Medyo maulan pa yata sa labas. All right, thank you everyone. Bye.
Thank you, sir.
Thank you po.
Bye, sir.
Bye, sir.